Welcome everyone. We are discussing combination. So today I will discuss a theorem relating combination. Selection of n different things taking any number at a time equals to 2 to the power n minus 1. 2 to the power n minus 1. Selection of n different things taking any number at a time. So any number means we can take at least one, that is 1 at a time, 2 at a time, 3 at a time, or all at a time. So out of n things we can select 1 or 2 or 3 or all, that is n at a time. So all out of n things we can select n. So number of possible selections. Equals to NC1, NC2, NC3, NCn. I have already stated there is a result of binomial theorem. In previous class I have already stated, and this is equal to 2 to the power n minus 1. NC0, NC1, NCn equals to 2 to the power n, NC0 equals to 1. So if you take it right hand side, so result will be 2 to the power n minus 1. So this is our desired result. Now using this theory, we solve some problem of this chapter. So this is our working tool, 2 to the power n minus 1. So problem number 1. A man has 7 relatives. In how many ways can he invite one or more in a dinner party? So 6 relatives. So out of 6 relatives, he can invite 1 or 2 or 3 or all at a time. So number of possible selections equals to 6C1, 6C2, 6C3, 6C4, 6C5, and finally 6C6. At least 1. So 1 or 2 or 3 or 4 or 5. So by well-known result, this is 2 to the power n minus 1. So 2 to the power 6 minus 1. So this is also problem of WBJEE. Very simple problem. So I am discussing combination, the chapter, the problem of combination, by dividing it into several parts. I will take 10 to 12 classes for this chapter. So look, problem number 2. There are 15 bulbs in a room. Each of them can be operated independently. That is 15 switches. The number of ways in which room can be illuminated. So 15 bulbs. A room is illuminated means The room can be illuminated by switching on one light or two light or three light or all the light. Our main aim is to illuminate the room. So one light, the room is illuminated. For two light also, for three light, for all. So we are not interested about sufficient number of light. So number of possible selections equals to, out of 15 bulbs we can switch on one or two at a time or three at a time or all at a time. So this is 2 to the power 15 minus 1. 2 to the power 15 minus 1. So this is our answer. Now see which one is correct possible answer for this problem of WBJE. Now this is all are in terms of 8. So we can write 2 cube into 5 minus 1. So 8 to the power 5 minus 1. So problem case A is possible answer. Now next problem, one more simple problem. How many different factors can 210 have? 210 have. So for example, for 12, so what are the factors? 1, 2, 3. Now taking 2 at a time, 2 into 2, 4. 2 into 3, 6. 3 into 1, 3. So it is, and taking 3 at a time, this is 12. So you know factor of 12s are 1, 2, 3, 4, 6, 12. So how many factors? 1, 2, 3, so 6 factors. 6 factors. So if number is greater, so what is the rule of finding factors? So look, 2, 1, 0, 2, 1, 0, 1, 0, 5, 3, 5, 5, 7. So prime factors are 2, 3, 5, 7, each occurring once, no repetition. We are considering different cases. So we are not taking 1 because 1 is not prime factor. So out of these 4 factors, we can take 1 at a time, or 2 at a time, or 3 at a time, or 4 at a time. So factors are total factors. 4C1, 4C2, 4C3, 4C4. So 4C1 is 4, 4C2 is 6, 4C3 again 4, this is 1. So 15 factors. Now look, here, note, here the factor 1 is excluded. One is excluded because we are not taking consideration of 1 because 1 is neither prime nor composite. But the number itself is included. So the factor 1 is excluded, but 210 is included. So you must look the language. So how many different factors 210 have? So here 15, but 1 is excluded, 200 is included. If language is like this, find different factors including 1 and 210. Then you have to plus 1. So factor will be 16. Excluding 1 and 210. Then 15 minus 1, that is 14. So if it is given, find number of proper factors of 210. Proper factor means 1 and 210 are excluded. In this case, answer will be 15 minus 1, that is 14. So you should keep in mind about the language. So in the next class, I consider number of factors when look these prime factors are repeating factor. In this class, we are considering only different factor. Now we consider one more problem. Now consider problem number 4 and 5. They are same type but slightly different. From 4 apples, 5 oranges and 3 mangoes, how many selection of fruits can be made, taking at least one of each kind, if fruits of same kind are different shapes? So apples, they are of different shapes. So we can recognize one apple from another apple. That is, they are different. And one language here, at least one of each kind. So from 4 apples, at least one can be selected in 2 to the power 4 minus 1 equals to 15 ways. At least one. Formula is 2 to the power n minus 1. Now from 5 oranges, at least one can be selected in 2 to the power 5 minus 1 equals to 31 ways. And from 3 mangoes, this is oranges, at least one can be selected in 2 to the power 3 minus 1, so 7 ways, taking at least one from each kind. So by a PC, total number of selections. Total number of selections equals to 15 into 31 into 7. 15 into 31 into 7 ways. So this will be answer. So very simple. Now consider problem number 5. So 5. So look, find total number of selection taking at least one green ball and at least one blue ball from 5 different green balls. So look here, from it is green, 5 different green balls. At least one can be selected in 2 to the power 5 minus 1. So 31 ways. 5 different green. From 4 different blue balls. Add list. Look at the language. Add list 1 green and add list 1 blue. So from 4 blue balls, at least 1 blue can be selected in 2 to the power 4 minus 1 equals to 17 way. Now look at the language. There are 3 different red balls, but here restriction is not given that you have to take at least 1 red ball. This is the only difference. So here restriction is not imposed. So from 3 different red balls, number of possible selection equals to 4C0, 4C1, 4C3, 4C2, 4C3, 4C4. Look, we can take no red balls because we have already selected any one of green, any one of blue balls. So here this restriction is not given. So we cannot take any one of this, or take 1 or 2 or 3 or 4. So this is 2 to the power 4, 16 ways. So this is the only difference. Here restriction was not given to red balls. So then by FPC, number of possible selections. So 31 into 17 into 16. So this will be our answer. So you should be cautious about language. So look, minor change only. There is no restriction on red balls. Next, now we consider 2 most important problem of competition. So look, the ratio of total number of selection of 2n different things to the total number of combination of n different things be 1025:1, find n. So look, we use the previous theory. Selection of 2n different things from 2n different things. Selection of 2n different things. So selection of So we can select out of 2n things 1 or 2 or 3 or maximum 2n. So selection of, you have to select at least one. Selection of at least one thing from 2n different things equals to 2 to the power 2n minus 1. Then to the total number of combination, that is selection. We can write it selection because first one is given selections. So selections of at least one thing from n different things equals to 2 to the power n minus 1. So this is our formula. N is replaced by 2n. So given condition, given 2 to the power 2n minus 1 by 2 to the power n minus 1 equals to 1025 by 1. So we have to solve this equation. So if we factorize, look, a minus b, a plus b by 2 to the power n minus 1, 1025. So this one is cancelled out. So this implies 2 to the power n plus 1, 1024. So 2 to the power n equals to 1024. This implies n equals to 10 because it is 2 to the power 10. 1 GB. So what is n? N is 10. So simple problem. So very simple problem. You need only this formula. Next, second one. Look at the language. Here two restrictions are given. A person is permitted to select at least one and at most n. At least one, maximum n from collection of 2n plus 1 things, and this is equal to 255. Find value of n. So it is at least 1 and maximum n. So you can take 1 or 2 or 3 up to n because maximum n, not greater than n. So selections of 2n plus 1 things taking at least 1 and at most n things equals to 2n plus 1 C1, 2n plus 1 C2, 2n plus 1 C3, and maximum this is 2n plus 1 Cn. This is maximum, and this one is given by 255. So we have to solve this equation. 2n plus 1 C1, 2n plus 1 C2, 2n plus 1 C3, 2n plus 1 Cn equals to 255. So our main aim is to solve this equation. Now look, I have already stated there is a result of binomial theorem relating coefficient. So 2n plus 1 C0, 2n plus 1 C1, 2n plus 1 C2, 2n plus 1 Cn, 2n plus 1 Cn plus 1, and finally 2n plus 1 C2n plus 1 equals to 2 to the power 2n plus 1. So result is NC0, NC1, NCn equals to 2 to the power n. So n is replaced by 2n plus 1. So this is our result. Now here up to n is given. So there is also a result of complementary combination theorem, NCR equals to NCn minus R. So look, here 0 is not given. So 2nc 0, 2n plus 1 c 0, 2n plus 1 c 1, 2n plus 1 cn. And by complementary combination theorem, so 2n plus 1, if you subtract it, it is 2n plus. If it is, next one is 2n plus 1, look, next one is 2n plus 1 c, n plus 2. So if you subtract it, this will be 2n plus 1 c, n minus 1. So this is 2n plus 1 c n minus 1. And finally, last one will be 2n plus 1 c 0, c 0. And this is c 0, c 0. And this is 0, so this one is obviously c1 equals to 2 to the power 2n plus 1. Now look, we are getting this and this as same term. So 2 common, 2n plus 1 c0, 2n plus 1 c1, and dot dot this and this added, 2n plus 1 cn equals to 255. 255. Now, look, this is 2 and 2n plus 1 c0 is 1. And from this to this, this one is given as 255. 255. So sorry, this one is 2 to the power 2n plus 1. So 2 into this one is 1, and from this to this, by our well known result 1, this is 255. So this is equal to 2 to the power 2n plus 1. Now this is 256. So 1 plus 255, that is 256. 256 equals to 2 to the power 2n. 2 to the power 2n. So this is 2 to the power 5, this is 32, then 64, 1 to 8, 6, 7, 8 to 56. So 2 to the power 8 equals to 2 to the power 2n. So n equals to 2n equals to 8, so n equals to 4. So we need here a result of binomial coefficient. So listen again, add list 1, 2n plus 1 c1, 2n plus 1 c2, 2n plus 1 c3, and add most n equals to 255. So this is our given result. And from binomial coefficient we get this result. Then using complementary combination theorem, NCR equals to NCn minus R. So up to this is unchanged, but this one is, if you subtract it, 2ncn, then 2ncn minus 1, and last one is 2nc0. We are getting all term 2 times. So 2 common, put the values and you get n equals to 4. So this is most important problem for competitive exam. So today, through this video, we have solved some important and interesting problem also of combination when things are different and we are taking any number of things. Thank you for today.